Hello everyone, I'm Dongjie He. Today I will introduce loops in flow graphs. The content is abstracted from the classic book, Compiler Principles, Techniques, and Tools. In this lesson, we will learn two things. We will first learn what is a natural loop, and then introduce the algorithms for finding the natural loops in a flow graph. First, what is a loop? In the internal of a compiler, the source program is often translated into an intermediate representation called the flow graph. Take a look at the example code below. The program written in the C language in the left box is translated into a flow graph in the right hand. A flow graph is a directed graph. It has only one single entry node, and every other node in the graph is reachable from the entry. That means you can always find a path from entry to any given node in the flow graph. There are maybe many cycles in the flow graph, but from the compiler optimization perspective, not every cycle can be called a loop. Take a look at this flow graph. There are two cycles. One is formed by A, C, and D, and the other is formed by C and D. Here, A, C, D cannot be called a loop because it has two entries, node A and node C. So there are some intuitive properties of a loop. A loop should have only a single entry point, and the edges in the loop must form at least one cycle. One question you may want to know is why compilers need to identify loops. In other words, what are the benefits of identifying loops? The loops are not sensitive to input syntax, so that the compiler optimization techniques can give a uniform treatment for all loops, including those caused by the do, while, for statements, and loops caused by the goto statements. Before defining the natural loop, we first introduce an important concept called dominators. In a flow graph, node X dominates node Y. We write as X dom Y if and only if every path from the entry node to Y goes through X. Let's take a look at the flow graph here. According to the definition, we have the following facts. First, every node in the graph dominates itself. That is because every path from the entry to the node must go through the node itself. And second, the entry node dominates all nodes in the flow graph. This is determined by the definition of the flow graph. And last, we have node C dominates node D. As you can see from the flow graph, every path from the entry node to node D must first go through node C. Okay, now let's define the natural loops. A natural loop first has a single entry point called header. The header dominates all nodes in the loop. That means if you want to visit any nodes inside the loop, you must first go through the header node. A natural loop also has a back edge. The back edge is an arc edge such that its head dominates its tail. The back edge must be a part of at least one loop. The natural loop of a back edge is the smallest set of nodes that includes the head and tail of the back edge and has no predecessors outside the set, except for the predecessors of the header. Let's review the flow graph presented in the previous slide. In this flow graph, we have two cycles, ACD and CD. Is ACD a loop? In this cycle, both node A and node C are the entry node of the loop, so it has two entry nodes, while a loop only has one single entry point. So it's not a loop. Is CD a loop? Yes, it's a loop. C is the head node and it dominates the node D, and DC is a package. Okay, we have learned the definition of the natural loop, and now we start to learn the algorithms for finding the natural loop. There are 3 steps in total. Step 1, we will learn how to compute dominator relations between the graph nodes, and this relationship of dominator will shortly be used in step 2. In step 2, we will identify packages, and in step 3, we will introduce how to construct the natural loops of a package. Okay, let's first go into step 1, finding dominators. According to the definition, a node X dominates a node Y in a flow graph if and only if every path from the entry node to Y goes through X. So how to finding the dominators? We can formulate the problem as a MOP, data flow analysis problem. We first define 2 functions, the in X and out X. Let in X be the nodes lie on a path reaching node X exclusively that dominate X. And let out X be the nodes lie on a path reaching node X inclusively that dominate X. So according to the definition, we have the following transfer function. We will use the pictures here to illustrate the transfer function. Given a node X, the in X is the value right before the node X, and the out X is the value right after the node X. So we can easily get the first transfer function, the out X equal to in X plus the X itself, because X also dominates X itself. And we can compute the in X by intersecting the out value of all its predecessors. That is because the dominators of all the nodes before X must be in all paths that also dominate X. So it must be the intersection of the out value of its predecessors. Lastly, we give the initialization of the data flow analysis. We state the in value of the entry to be an empty set and set all values of the out values of all other nodes to be n, where n is the full state of the nodes in the flow graph. Let's see an example. We still use the flow graph used in previous slides. We first set the in value of the entry to be empty, and the out value of all the nodes in the flow graph to be n, where n is the full state of the flow graph, which is entry A, B, C, and D. So initially we use the first transfer function. We get the out value of the entry to be a set with a single item entry, and next we compute the in and out value of node A. As you can see from the flow graph, the predecessors of node A is entry and node D. So its in value is the intersection of its the out value of its predecessors. That is entry C and entry. It's n and entry, so the intersection is should be entry. And use the first transfer function, we get the out value of A to be entry and A. And similarly, we can compute the in and out value for other nodes. And the results is here. Once the first pass is finished, the data flow analysis is done. So from the results, we can see that entry node dominates all the nodes in the flow graph, and every node dominates itself. And lastly, we have the node C. C dominates node D. Now we analyze the performance of the data flow analysis. Given a flow graph, we could compute its post order. For the flow graph here, its post order is entry A, B, C, and D, and the reverse post order is the reverse of the sequence. That is D, C, B, A, and entry. If we compute the data flow analysis according to the reverse order, most flow graphs can converge in one pass. Okay, now let's go to the step 2, finding back edges. Given a flow graph, we first traverse its edges in a depth-first search, which forms a depth-first spanning tree. For example, given the following flow graph, we can go a depth-first search, and the red edges forms a depth-first spanning tree. With this depth-first spanning tree, we can categorize edges in the flow graph. The red edges are called the advancing edges. That is the edges are always from the ancestors of the tree to its proper descendant. And the blue edges are called the retreating edges, which are from the descendant to the ancestors. And the other edges are called the crossing edges. For example, the AC edge in this flow graph is a crossing edge. Okay, now we can give the definition of a back edge. A back edge is such a kind of edge whose head always dominates its tail. Next we analyze the relationships between graph edges and the back edges. We can get the following conclusion: the back edges cannot be any advancing edges and crossing edges. That's because the advancing edges and crossing edges are always from the ancestors to the predecessors in the spanning trees, so their tails can not dominate its headers. So back edge can only be found from the retreating edges. Below gives the algorithms. It's quite simple. For each retreating edges in the flow graph, we check whether their head dominates their heel by using the dominant relationships computed in the step 1. Let's review the blue edges in the flow graph here. All the 4 blue edges, DC, GD, J to G, and H to C, are all back edges. Okay, now we go into the step 3, constructing natural loops for a back edge. The natural loop of a back edge is the smallest set of nodes that includes the head and tail of the back edge and has no predecessors outside the set, except for the predecessor of the header. So the algorithm is quite simple. We can use the reachability analysis to construct the natural loops for a back edge. Given a back edge, we obtain G prime by deleting the node head from the flow graph G. And then with the G prime, we can obtain a new set node called N to be the node, those nodes in G prime that can reach tail T, and the nodes in N plus node H forms the natural loop of the back edge T to H. Let's see an example. We still use the flow graph used in previous slides, G, and we check how to construct the natural loop for the back edge DC. We first delete node C in G and obtain the G prime here. And in this flow graph, all the nodes that can reach the tail node D are shaded in red. So the nodes in the shadow plus the head node C forms the loop, which is C, D, E, F, G, H, and J. And similarly, the loop of other bucket edges can be constructed similarly. At last, we investigate the relationship between loops. If two loops do not have the same header, then they are either disjoint or one is entirely contained or nested within the other. We call the inner loop and outer loop. If two loops share the same header, it's hard to tell which is the inner loop and which is outer loop. So we can combine them as one. Look at the graph below. It has two loops, A, B, and AC. The two loops share the same header A, so we can combine them as one. Such kinds of flowgram often appears in a program that has a loop with a if and else branch in it. Okay, we have finished the content of this lesson. Let's briefly summarize this lesson. In this lesson, we first define what is a loop. A loop has a single entry that dominates all nodes in the loop. It also has a bucket edge whose head dominates its tails. And next, we introduce the algorithms for finding the loops in the flow graph. The algorithm has 3 steps. In the first step, we use a data flow analysis to compute the dominator relations between the graph nodes. And in the second step, we exploit the depth first spanning tree to categorize the edges in a flow graph and introduce how to identify the bucket edges from the retreating edges. And lastly, we use the reachability analysis to construct a next loop of a bucket edge. Okay, lastly, here is an exercise for thinking. A flow graph usually has multiple deep first spanning trees. And our algorithm introduced in this lesson can guarantee to always find the same loops. Why? I can give you a hint. That is, the bucket edge finds in different spanning trees are always same. Okay, that's all for this lesson. Thanks for listening. Bye bye.